The operational amplifier, or op-amp, is a very significant component in analog electronics. It provides a building block for amplification. Here is the op-amp page in Wikipedia, and here we have a circuit symbol for an op-amp. It has two inputs, an inverting input with a minus and a non-inverting input with a plus. And it takes this differential voltage between these two and amplifies it to the output. Now, amplification is the linear multiplication of whatever the input, this differential voltage is, multiplied by an amplification factor, A, which sets the slope of this line. Now, the problem with this is that high amplification, you can get near infinite values required for the output. So the solution of the op-amp is to limit the output beyond certain bounds here, from minus 15 volts to plus 15 volts. It only amplifies linearly in the range until saturation. Back to the wiki page, the ideal op-amp only has two inputs, but a real op-amp here has an additional set of inputs. The signal inputs are in the range of 5 volts, but these power inputs are from plus 15 volts to minus 15 volts, and these provide the power for the amplification. Now let's take a look at Paul Falstad's most excellent circuit simulator applet. So let's draw active building block op-amp, ideal, and here we have an op-amp. Let's provide it with a couple of inputs and sources, add variable voltage, and we'll say here's a variable voltage, and here's another variable voltage. As we create these voltages, you'll see over here on the right, there are sliders that adjust the actual magnitude of the voltage. Now we'll add a couple of resistors. Add resistor R. Here's a resistor in here and a resistor in here. And now we'll right-click here to add a scope to view the output of the op-amp while we play around with the values of the input. Now take a look. If the non-inverting input is greater than the inverting input, then the output here is plus 15, the maximum positive value. If the non-inverting input is less than the inverting input, then we get minus 15, the maximum negative value. So here we see the comparator function of the op-amp, that it just compares the two voltages on its inputs and gives a maximum or minimum output based on those relative values. To get the linear response that we want from our op-amp, we need to add a wire. Here we can either do draw, add wire, or we can hit the W key, and we'll add a wire that goes up here from the output across over to the inverting input. This is a negative feedback control. And take a look at our output voltage now. Instead of being an abrupt bang bang from one extreme to the next, we get a kind of linear amplification of the difference between the two inputs. And this had me confused. How does that negative feedback work? To clarify the principles here in my own mind, I created a hydraulic analogy for the op-amp. Here is my op-amp hydraulic analogy. It's a Python program available on my GitHub site. And here we have the two inputs. This is the non-inverting input, and the other one is the inverting input. And these feed into a cylinder either side of this blue piston, and when the non-inverting input is greater than the inverting input, the piston slams to the left, whereas when the inverting input is greater than the non-inverting input, it slams over to the right. Now I'm going to pause the simulation here so I can move the piston directly with this slider and take a look at the red bar either side of the piston. And it is a valve on the right and a valve on the left connected to the plus 15 volt on the right and the minus 15 volt on the left in such a way that when the piston slides to the left, it closes the minus 15 valve and opens the plus 15 valve, whereas when it slides the other way, it closes the plus power and opens the minus power. Now, if I turn on this function line, you can see that although there's a bang-bang comparator performance beyond this limit, right in the middle there's a little linear range where the output is proportional to this input. So back to Fallstad, I've added a switch here into this feedback loop, and when the switch is open, then we get the bang-bang comparator type behavior as we expect. But when we close the switch and turn on the feedback mode, take a look at the output down here in the trace, and it's now a proportional output. It looks like a low voltage, but that's because it's automatically scaling. So back to my hydraulic analogy, we'll go to the op-amp analog with feedback, and we'll run that. And here we have the same arrangement as before, but now we have a feedback connection with a valve from the output back to the inverting input. So if I have the valve closed, we get that bang-bang kind of comparator function going on. But if I open the feedback valve, now you'll see that the output grows or shrinks proportionate with the input. In fact, if I move the inverting input to 0, then the output becomes proportionate to the input. And if I close the valve, it goes back to the bang-bang behavior. Now let's take a closer look at what's going on here. If I increase the non-inverting input, the increased pressure pushes the piston to the left. But as it does so, it also opens up the valve to the positive power input here. And with the feedback, some of that increased pressure comes back to the inverting input and increases the pressure to the left side of the piston, stopping it from advancing further left. In fact, the piston will always move to a point where the pressure is balanced on both sides of it. It's a classic negative feedback operation. So the function line does not really need to be strictly linear in the middle. A more realistic function would be this, a smoother function, but as long as it's downwardly continuous. Back to Fallstad's simulator, I fixed this plot so it no longer rescales automatically. These are 5 volts per division. And we're operating here in regular feedback mode. If I turn the inverting input to 0, then the output is a follower, that it will follow the non-inverting input. So here we see the voltage changing, and here we see the buffered voltage on the output. So what's the use of a follower that just follows the voltage of the input? Well, to demonstrate this, I'm going to add a switch here and a resistor and the ground. And now what we've done is we've applied a load to this output. If I flip this switch open and closed, you can see that whether or not I've applied the load, the voltage remains stable and it still does its analog following function. So this is functioning like a buffer to make sure that the output stays what it is by this negative feedback, independent of the load that you may put on it. Now, let's erase these components and create a resistor. Right-click, edit, and make it 10K. If I replace this feedback line with this 10K resistor, look what happened to the output. It jumped way up because now with a resistor on the feedback, this makes a voltage drop from one side to the other, which means that the op-amp has to give more amplification to overcome the load on the feedback line. And now we have this output bolstered to 5, 10, 15 volts. Up to 15 volts, it acts as a follower, but of course it cannot amplify beyond 15 volts for the output. So this is now a true amplifier that's actually amplifying the voltage on the input, adjustable by the value of this resistor. So that's my hydraulic analogy to give you an intuitive understanding of the operational principles behind the operational amplifier.